Hey, welcome back to Calculus. In this first day of section 6.4, we're going to we're going to look at an application of the definite integral to physics. And namely, we're going to check out this quantity in physics called work. Okay, so the objectives for the lecture are written there in front of you. Let's kind of go over them together here. I want to define what I mean by work. If you're not familiar with it, we'll give a definition, talk about what units it's measured in, depending on how you're measuring force and distance. Or work has different units. The notion of work that we're going to give a definition for at the beginning will require the force to be constant and acting in the direction of motion. So if we're going to take a non-constant force acting in the direction of motion, then we need an integral to compute the work. So we're going to derive that integral in this lecture. And then our primary illustration of this will be to spring mass systems. We'll look at something called Hooke's law. Okay. So that's kind of an outline of our agenda. Let's get going here. Let's start by talking about units. You may have had a physics course or just from sort of coffee table physics have become familiar with something called Newton's second law. Newton's second law says the force acting on an object in motion is equal to that object's mass times the object's acceleration. So here, m, I'm denoting the mass of the object. And how do you measure mass? Well, in the SI unit system, mass is measured in kilograms. So unit of mass is the unit of kilogram. I mean, you can talk about grams and so on, but we're going to measure mass in these units just to keep all of our work uniform. So if we're working in the SI system, we'll measure mass in kilograms. In the US system, or the so-called just US unit systems. Mass is measured in a unit that we really don't talk about in colloquial English very much. It's called slugs. Okay, and you multiply that mass by the acceleration. The acceleration in the SI system is measured in meters per second squared. In the US system, it would be measured in feet per second squared. So the product of those things is force. Okay, so in the SI system, if you multiply kilograms by meters per second squared. I mean, you can certainly pronounce this thing kilogram meter per second squared, but a shorthand, another name for that thing, it's called a Newton. Okay, so the SI unit of force is a Newton. It's kilogram meters per second squared. 1 Newton is the force required to accelerate a mass of 1 kilogram, 1 meter per second squared, if you like. So that's the unit of force in the SI system. The unit of force in the US system is going to sound more familiar because it's kind of how we speak about them. We never say slug feet per second squared. It sounds a little weird. We call that unit of force a pound. Okay, so maybe it's worth taking just a real quick second here to say that in colloquial English, pounds and kilograms get treated like they measure the same thing, right? Maybe you have a bathroom scale and you can set it to give your weight in pounds or your weight in kilograms. But more precisely, in scientific calculations, and in particular in this course and in this section, kilogram and pound are not the same kind of quantity. Okay, a kilogram is a unit of mass. And if you want to get the corresponding force, something that's analogous to pounds, you have to multiply that unit of mass by the acceleration. Okay, pound is a unit of force. The multiplication of the acceleration and the mass is already been done. So if we were working in colloquial English consistently, our bathroom scale would say how many kilograms and how many slugs we weigh, right? That would give us both those units of mass. Or the bathroom scale would tell us how many pounds we weigh or how many newtons we weigh. But in colloquial English, we kind of interchange kilograms and pounds. And it's forgivable because here on our planet, Earth, acceleration of gravity is what the primary force there involved, and that acceleration is constant. If you speak about kilograms, it gives you kind of enough information. If we were all to travel to the moon, our mass in kilograms would stay the same, but our weight in newtons or pounds would be less because the acceleration of gravity on the moon is less. Okay, so those are just little comments about the units of force. And now let's give the primary definition of work. So this definition is kind of loaded. We have to be careful. So if we have a constant acceleration, so we have a force that's constant and acting in the direction of motion, then the work done by that force in moving an object d units The units would be meters in the SI system, feet in the US system. The work is defined to be the force times the distance. Okay, so again, it's force times distance when you have a constant force. So it's a constant force acting in the direction of motion. Work is force times distance. We can write in the units here. We said that the units of force are called newtons in the SI system. The units on distance would be meters. And so the author is writing it down here. I'll highlight it so it's easier to see. The unit on work, you could just pronounce it Newton meter. All right, so it's a Newton times meter, it's a Newton meter. That has a synonym, it's also called a joule. Okay, so 1 joule is 1 Newton meter. It's a unit of work. If we're measuring the force in pounds, then the distance would be measured in feet. So we just call the units on work foot pounds. Okay, 1 foot pound, the author has calculated for us, is approximately 1.36 joules. Okay, good. So that's the definition of work. It requires a constant force acting in the direction of motion. This is a real quick example. This is example 1 from your text. I borrowed it so I don't have to write it out. It looks nicer anyway. So let's look at, both these problems are about lifting an object that has a fixed mass and therefore near the surface of the earth, a fixed weight. Okay, so when you're lifting an object, the force that's required is the force to overcome gravity, right? And you're moving in the direction of motion because you're lifting it up. So our requirements are satisfied. When you're lifting a book or some other object near the surface of the earth straight up, then the force required is the force to overcome gravity. And since you're lifting it straight up, that force is acting in the direction of motion. So let's look at part A first here. So we're going to lift a 1.2 kilogram book off the floor and put it on a desk that's 0.7 meters high. Okay, how much work? That's what we want to know. How much work is done in doing that? Okay, well, work is force times distance. The only little rub here in this example is that you should not use the mass in kilograms as a force. Yeah, the mass in kilograms, that 1.2, needs to get multiplied by the acceleration of gravity, which the author is asking us to use 9.8 meters per second squared. So together, the acceleration of gravity and the mass give you the force. Okay, so that red underlined quantity, 9.8 times 1.2, would be the force in newtons, and we're multiplying that by 0.7 meters, right? Because that's how far we're lifting the book. And if you get out your calculator, stop the video, check my math, I calculated that as 8.2 approximately Newton meters, or 8.2 joules. Okay, so you got to remember that you have to build in the acceleration of gravity if you're given the mass in kilograms, because those two things together, sorry about that, those two things together make the force. Okay, so force times distance. In part B, we can relax a little bit. Part B, how much work is in lifting a 20-pound weight 6 feet off the ground? Well, the 20 pounds is already a force. The acceleration of gravity is built in. You don't have to worry about multiplying it by anything. So I just take my 20 pounds, multiply it by 6 feet, it's 120 foot-pounds. Nice. Those aren't calculus problems, right? That's if the constant force is acting in the direction of motion, the calculation of work is not a calculus problem, it's a multiplication problem. So why are we talking about it in our calculus class? Well, because I want to answer the question, what if the force isn't constant? What if you have a non-constant force, f of x, right? So the magnitude of the force depends on some variable x, and it's moving an object. It's acting in the direction of motion. We won't relax that. You'll have to take Calc 3 if you want to learn how to calculate work when the force is acting in a direction of other than the direction of motion. But if we have a non-constant force acting in the direction of motion and it moves an object, say from x equals a to x equals b, so the displacement would be, assuming b is bigger than a, b minus a units, either feet or meters. The question is, well, how much work, right? It's not a multiplication problem because the force isn't constant. But here's the big idea in calculus. This is the part of calculus that I want you to remember for the rest of your life, that you make a local estimate. If you assume over a small piece of displacement that the force is approximately constant, that is, that it's a continuous function, then you can locally estimate the work, and then you can add those local estimates together to give an estimate. All right. So I'm just kind of putting some notation in here for some small interval containing a point xi star. The force f of xi star is approximately constant. So the work in moving the object over that little interval that contains xi star would be approximately f of xi star times delta x. Delta x is the width of the interval. Yeah. So this is force times distance is work. Why is it approximate? Well, because the force really isn't constant, but I'm pretending it is. If delta x is small, the approximation is sharp. Okay, adding those things together gives us one of our Riemann sums. Yeah, what am I saying in this notation down here that I'm highlighting now? I'm just saying if you took the work done by this force and moving it across each little subinterval and added them all together, you should get a total for the work. The equation number is just because in the book this thing is equation 3, and I'm going to reference it in the slide below. All right, so we've got our Riemann sum. What do? You take limits as delta x goes to 0 of a Riemann sum, and you get some integral, right? So you can look at the paragraph if you want there, but the kind of summary is in this box down here. If a non-constant force is acting in the direction of motion, and it's displacing an object from point A to B along the direction of motion, then the work done by that force is the integral of the force with respect to distance. Okay, work is the integral of force with respect to distance. If the force is a constant, that integral would just be the constant times the width of the interval, that is force times distance. It recovers our previous formula. So this is a slight generalization of it. Let's do two examples. One, I'm just going to kind of give you this artificial force function just to kind of let your eyes get used to these calculations. The second one, we're going to have to derive from a little physical principle what the force function is. So this is example 2. It's also example 2 in this section in the book if you want to check it out there instead of here. So what are we given? We're given a particle that's x feet from the origin. A force acts on it by this formula. So there's our non-constant force, right? So according to this formula, the further you are from the origin, the more force is acting on you. The force acting on you is x squared plus 2x, and it's in pounds. Yeah. It's in pounds. It's given in the problem. Okay, so we're measuring distance in feet. We're measuring force in pounds. Cool. So that's our force over this interval from 1 to 3. How much work in moving it from 1 to 3? Well, by definition, it's this integral. It's the integral from 1 to 3 of our force function with respect to distance. That's a polynomial function. I've written its antiderivative down here. I'm skipping the details, but if you evaluate that thing at 3, subtract its value at 1, I'll let you verify that you get 50 over 3. 50 over 3 foot-pounds, slightly less than 17 foot-pounds of work. Okay, so that's just a generic example to give you the spirit of this stuff. If you have a non-constant force acting in the direction of motion, the work done in moving the particle from x equals something to x equals something is the integral. Nice. One more example. Trying to keep this video kind of short. It's a problem from physics about a spring. Yeah, if you've ever pulled or pushed on a spring, you've probably made the following observation, that the more you pull the spring out of equilibrium, I mean, springs have an equilibrium, a natural length. You can see it on the right-hand side of this picture here. This spring is sort of attached to a wall. So think of this thing I'm highlighting in red as fixed. It's unmovable. We're ignoring all other forces, so no friction, no air resistance, nothing like that. So if you just let a spring go, depending on what it's made out of and how tightly it's wound, it has some natural length. And we're calling that the natural position, or I also like to call it equilibrium. Okay, equilibrium is its natural length. And we're coordinatizing this problem. When a spring is in equilibrium, we're going to call its displacement from equilibrium x equal to 0. All right, so the variable x here is measuring the displacement out of equilibrium with the convention that Positive displacement means you've stretched the spring, like shown in the picture down below. A negative displacement, if I'm telling you that I've displaced a spring -1 foot or something like that, it means I've compressed it. Okay, so negative displacements, displacements that are less than 0, mean you're compressing the spring. And if you've ever pulled or pushed on a spring, you've probably noticed that the more you pull on it or push on it out of equilibrium, the harder it gets to do that. Yeah, pulling a spring, the first kind of, centimeter or so out of equilibrium is easier than the next centimeter, which is easier than the next centimeter. Eventually, the system would break down and the spring would break. But if as you pull on a spring, it kind of pulls back, quote unquote, harder and harder. So the physical principle that we're going to study here is something called Hooke's law, named after an English mathematician physicist, Hooke. And Hooke's law says that the force required to stretch a spring x units out of equilibrium is proportional to x. That is, the force is some constant times x, and that constant is called the spring constant. All right, so pulling a spring x units out of equilibrium requires a force of kx. K is a spring constant, it depends on the spring. So therefore, the work, if we run it together, the work is just the integral of f of x dx. That is, to stretch it from x equals a to x equals b. That is the integral of kx dx. Nice. How do you find the spring constant? Well, you need to know the force required to stretch the spring some amount. Sorry, I didn't realize my lines were still on the paper. Let me get rid of them. Last example. I've got this worked out. I can just narrate it through you. So we're given that it takes 40 newtons of force to hold a spring that's been stretched from its natural length of 10 centimeters to a length of 15 centimeters. So we've stretched the spring 5 centimeters. Be careful here. Be careful about this. Our formulas require that we measure distance in meters. So we're going to have to do conversions. When the author is giving us things in newtons and centimeters, we have to convert those centimeter lengths to meters. So in particular, 10 centimeters is 1/10 of a meter, and 15 centimeters is 0.15, right? According to our convention, natural length, that's x equals 0 meters. So we've stretched this spring 0.05 meters. We stretched it from 10 to 15, that's 5 centimeters, that's 0.05 meters. So here's how you find K. You find K, we were told that it takes 40 newtons to stretch this spring 0.05 meters. So because the force function is K times X, that gives us an equation, yeah? If we let x equal 0.05, that's the force according to Hooke's law, but that force is supposed to equal 40 newtons, right? Can solve that for K. Divide both sides by 0.05 and we get that K is 800. 800 what? Well, it's newtons per meter are the units on the spring constant, okay? So once you know the spring constant, then we know our force function. Our force function, let me just write it in here. Our force function is 800 times x newtons, where x is measured in meters. So if we want to know the work done in stretching it from 15 centimeters to 18 centimeters, be careful. You have to convert those things to meters. That's the work done stretching it from 0.05 meters to 0.08 meters. You're just integrating 800x. The antiderivative of that is 400x squared. And again, I'll let you check the arithmetic. That comes out to 1.56 joules. Okay, so there's a couple of examples illustrating how to use this principle that the integral of force with respect to distances work. In the next section, we're going to spend one more day in section 6.4. I want to show you some variations on kind of a lifting problem. Okay, so when you're lifting something that's mass is not remaining constant as you lift it. All right, thanks for listening.